Okay, so welcome back to this session on problem solving for fatigue design or fatigue failure of materials. So far we've looked at the situation wherein the loading is pretty much one-dimensional, wherein we've looked at the stress amplitude and mean stress for a given one stress component, primarily the normal stress component. So that's sort of uniaxial loading scenario. But in general, the machine components are usually subjected to a multi-axial state of loading. So in those scenarios, how do we actually go about dealing with the problems? So we've actually discussed this during the lectures, but now we will see a couple of problems which actually deal with multi-axial loading. So here we have a steel bar that has properties given as endurance strength 250 MPa, yield strength 410 MPa, and ultimate strength 500 MPa. And if this bar is subjected to a steady torsional stress of 50 MPa, a steady axial stress of 70 MPa, and an alternating bending stress of 80 MPa. So here you can see that the bar is subjected to a multi-axial loading because you have a shear stress as well as normal stress due to axial load and bending load. But the normal stress in bending is we have not been given whether in which plane is it acting, and hence we assume that the normal stress caused by bending as well as the axial stress are in the same direction. So in that sense, it becomes a two-dimensional problem. So basically, we are dealing with a multi-axial loading scenario, wherein you have a steady torsional stress. So I'm writing tau xy because we are saying steady, meaning it is time invariant. So we take this as a mean load. So mean load is sort of your static load, so that it does not change. So the torsional stress has a steady component of 50 MPa. And the alternating component, that means there is no amplitude to this, so the alternating component is 0, which means it is a static load. And then we have steady axial stress. The axial stress, I'm assuming it to be sigma xx, just to make it simpler. Otherwise, you could actually assume the axial stress caused by the axial loading could be in one direction and the bending stress could be in another direction, both of them being normal. So here I'm assuming that them to be same. Because it is steady, then it is mean stress, that is 70 MPa. And the alternating stress is 80 MPa. Okay, so these are the two things that we have in this kind of a loading scenario that we are talking about here. Okay, so now you have a mean stress and an alternating stress. So now I will drop my xy and xx because there are only two components. So I'm calling my shear component to be tau m equal to 50. I'm not writing the units because they're all consistent units, and tau a equal to 0. Sigma m is equal to 70. Sigma a is equal to 80. So one approach to, because we know how to deal with these problems when the given state of loading is one dimensional in nature. But now what we will do is we will try to convert this multi-axial state of loading into equivalent one-dimensional stress that we have learned during our static failure theories. That is, we can actually write a multi-axial state of loading into an equivalent one-dimensional quantity called equivalent stress or von Mises stress. Similarly, now we will try to find out the von Mises stress equivalent of these two components. So I need to find out the mean stress, equivalent mean stress. It is actually computed using the same formula, that is sigma m. Sorry, excuse me, I am using. Yeah, so just let me just bring this subscripts to down just to be consistent. I'm dropping x, y, all these things. So sigma m square plus 3 times tau m square. Right. This is our regular formula for finding equivalent stress. So here what I'm trying to find out, equivalent mean stress. This is what I call equivalent mean stress. So that would be equal to square root of sigma m square is 70 square, 3 times tau m square is 50 square. So if you would calculate that, that comes out to be 111.36 MPa. That is your equivalent mean stress. Similarly, I can calculate equivalent alternating stress or stress amplitude, equivalent stress amplitude or alternating stress. That would be square root of sigma a square plus 3 tau a square. You know that here in this case tau a equal to 0 and hence this becomes simply sigma a that is equal to 80 MPa. Okay, so the way to solve these multi-axial fatigue problems, there are other approaches. If you see different textbooks, they may find other approaches, but this is one of the approaches and simpler approach which has analogy between what we have done in the static failure theories, and hence we are adopting that particular approach. But there are slight variations in computing. How do you go about computing mean stress and so on? But that we will not discuss in this class. In this class, we will assume we will take this route of finding equivalent stress from the multi-axial state of stress. Okay, so now having found this multi-axial state of stress, now you need to find for this particular loading scenario, given these material properties, you need to find the factor of safety according to modified Goodman criterion. So what is modified Goodman criterion? Modified Goodman says that so the Goodman diagram is this, and then that is your SUT, and then let us say this is my SE, right? And then this is x-axis is sigma m, sorry, and this is y-axis is sigma a. So modified Goodman says that sigma m divided by SUT plus sigma a by sigma a by SE equal to 1 by factor of safety. That is our modified Goodman criteria, right? So since we are dealing with the multi-axial fatigue problem, so you replace sigma m with sigma m equivalent because it's one-dimensional scenario, and sigma a with sigma a equivalent, SE equal to 1 over n, right? That is the factor of safety. Therefore, your factor of safety can be written as SE SUT divided by sigma ME endurance strength sigma AE SUT. So that would be equal to sigma SE is the endurance strength or failure strength is 250 and SUT is 500 divided by sigma ME is 11,111.36 into SE is 250 plus sigma AE is 80 into SUT is equal to 500, right? So if you do this calculation, it comes out to be 1.843. So the factor of safety is 1.843 in this particular scenario, according to modified Goodman criteria. However, you note that here you are given yield strength of the material, but that's a additional data that has been provided that need not be used in this particular problem. So several times when you are dealing with the design problems, you may have additional data, and then you should know that you need to discard that additional data when it is not needed. Sometimes when we are dealing with design problems, you may have missing data. So that means some data is not being given to you. Then you need to assume such missing data. In this particular scenario, we only have some additional data, and then we need to discard that. We don't have to use that. Whenever there is a missing data, you need to make an appropriate assumption for the missing data. Okay. I think I hope this is clear. How do we go about solving a multi-axial fatigue problem? Okay, good. So now let us go to, so we have actually seen the case of stress concentration factor being used in your static failure theories. But when you come to fatigue failure theory, so you have something called a fatigue stress concentration factor, right? Because the fact that the loading is dynamic is scenario, you need to deal with fatigue stress concentration factor. So here is a problem. It's of course it's given as a one-dimensional problem, but the idea of this problem is to see how we can apply stress concentration factor in the case of fatigue loading. That is the objective of this problem. So the problem can be considered as stress concentration factor, fatigue stress concentration factor. That is the idea to show this example. Okay, so you have a steel shaft. Consider a steel shaft in bending with an ultimate strength of 690 MPa. So the steel shaft's ultimate strength is 690 MPa with a fillet radius of 3 mm, connecting 32 mm diameter with a 38 mm diameter. So you have basically a steel shaft which is having 32 mm diameter, and it is connected to a 38 mm diameter using a fillet. Okay, so that is how. So this, let us say this is your 32 mm and that is your 38 mm, and it is connected with a fillet. That fillet radius is 3 mm. So if you were to make it a little bit, so the idea is that you have a 32 mm shaft connected to a 38 mm part. Okay, and here you don't actually connect like this. You will have a fillet. We are actually talking about this fillet radius. That is what I am shown here. So this R is equal to 3 mm, and this is 32, and that is 38. So if this is the case, the question is, this is what would be the factor of safety against failure for life n greater than 1 million cycles at reversing stress of 200 MPa. If this guy is subjected to a reversing stress of 200 MPa, how do you go about finding the factor of safety according to using the fatigue failure criteria? Yes, sir, using the known information. Okay, so we know that if one way to do this is, so let's look at two methods. So the first one, method one, we know this is 690 MPa is the SUT. Okay, and now what is the endurance strength of this guy? SU dash is equal to 0.5 SUT, that is equal to 345 MPa. Okay, so one way to do that is, because of the fact that there is notch, this is unnotched endurance strength, but now you need to calculate the notched endurance strength. So notched endurance limit or endurance strength is what? So notched endurance strength SE is equal to SE dash by KF. What is KF? KF is your fatigue stress concentration factor. So how do we go about calculating the KF? KF is, we know KF is equal to 1 plus Q times KT minus 1, where KT is your theoretical stress concentration factor. And Q is your notch sensitivity. And this KT, by looking at, so this is subjected to pure bending, as because reversed bending stress, so it is subjected to M, and you have diameter D and small diameter, capital diameter D, and this is R. By knowing the properties of D by D and R by D, one can actually get KT from the charts. So KT for a given D by D and R by D, you can get the KT from the charts. Okay. Now what is Q? So you need to know, in order to calculate fatigue stress concentration factor, you need to know Q. So Q is equal to 1 plus, so 1 by 1 plus square root of A by R, where under root A is known as Neubauer's constant, which is given as a function of this depends on ultimate tensile strength of the material for states. Okay, so for the given dimensions, we know that the small d is equal to 32 mm, capital D is 38 mm, and R is equal to 3 mm. So by looking at the charts, the stress concentration factor charts available in various design data handbooks, you can see that R by D, for choice of R by D and small d by capital D, you will find that KT is equal to 1.65. Okay, you can actually look at the charts and then find out this value, as we have done in the class. And now, by knowing the ultimate strength of the material to be 690 MPa, you can find out that the Neubauer's constant, you can extract the Neubauer's constant. That is one way. Otherwise, by knowing the radius, so R by small d value, you can actually look at the chart and directly get the Q value. Or you can look at the Neubauer's constant and plug in the value of Neubauer constant and radius of the fillet we know, and then from that you can calculate Q. So for this given data, Q turns out to be 0.85. Okay. So, one moment. It is not Q not does not turn out to be 0.85. Your under root A is 0.85. So once you have square root A 0.85, then you can actually calculate your Q to be 1 by 1 plus square root 0.85 divided by 3. That turns out to be your Q turns out to be, from that your Q turns out to be 0.65. Therefore, your Kf is equal to 1 plus 0.65 times 1.65 minus 1. Right? That is your Kf. So that turns out to be 1 plus 0.65 times 0.65. So that is 1.4225. So 1.4225. So I'm writing as 423. Therefore, your notch endurance strength SE is equal to 345, that is SE dash, by 1.423. So that would be 345 divided by 1.423. So your endurance strength, the notch endurance strength of the material is 242.4 MPa. That is the notch endurance strength of the material. Now we need to find out the factor of safety. So we know that if you are in SN diagram, right? So this is a 10 power 6 cycles. This is 10 power 6. So now I need to find out the factor of safety. So this value is 242.4 MPa. Right? The stress that we have applied on the material. So this is a failure strength at 10 power 6 cycles. So again, factor of safety is equal to your SE divided by applied stress amplitude. What is applied stress amplitude? Applied stress amplitude is 200 MPa. So that is 242.4 divided by 200. That would be 242.4 by 200. That is 1.212 MPa. Okay, this is one way to solve the problem. That means you are actually, by using the notch, you are actually correcting for the endurance strength of the notch. There is another way to solve this problem, that is your method 2. Instead of taking the effect of notch on the material property, we will bring in the effect of notch on the stress concentration. So normally your far field stress that is applied is 200 MPa. So the actual stress experienced by the material point will be fatigue stress concentration factor times far field stress. Fatigue stress concentration factor was 1.423. So 1.423 into 200. Right? So 1.423 into 200 will be 284.6. Now my factor of safety would be uncorrected endurance strength divided by sigma A, that is 0.5 SUT, because now the effect of notch has been taken into the applied stress. So you don't do this double counting. So you will then, because the effect of notch has been taken into the applied stress, you just don't have to take that into the account of endurance strength of the material. So the endurance strength of the material is 345, uncorrected endurance strength divided by 284.6. So let us look at what that would be. 345 divided by 284.6. That would be again 1.212. Oh, sorry, I'm sorry. This should not be MPa. Factor of safety is 1.21. So the point here, whether you take approach 1, approach 2, you will get the factor of safety. In one case, you are accounting for the effect of notch in the material property itself. That means you are modifying the material property while keeping the far field stress as the stress that is being applied. Another way to do it is actually you account for the stress concentration through the applied stress. So you have some far field applied stress, but the actual stress experienced by the material is this. So this is actually a naturally better way to do that. And then you have a material property, and for that material property, you have an increased stress, and then this is how you calculate the factor of safety. Okay, so this is how we are going to account for factors of safety. And please note that here the factor of the stress concentration factor that is given is only in bending. In general, what you may have is if you have a multi-axial loading, you may have fatigue stress concentration factor for bending and fatigue stress concentration factor for torsion or shear. So then you need to account for them separately. Okay. So you need to be very careful when we are dealing with multi-axial loading with stress concentration factor. You have to multiply the appropriate stress concentration factor with the corresponding type of stress. That is very important to realize. Okay, so now let us look at the next problem. So you have a rotating shaft. It's made of 42 by 4 mm AISA 1018 hole drawn steel tubing and has a 6 mm diameter hole drilled transversely through it. Okay, so which means you have first let's draw the situation. So you have a shaft. Okay, and the shaft is actually a hollow shaft. Okay, and it has a 42 mm by 4. So that means this outer diameter is 42 mm. It is given as and you have an inner diameter. So that means you have another okay, so you have so this is inner diameter small d. And what is given is 4 mm is the wall thickness. So 42 by 4 actually means that capital D is equal to 42 mm and the wall thickness, that means this guy is 4 mm. So that implies small d is equal to 42 minus 2 into 4. That is 34 mm. That's what it means. And this guy has a transversely what you call drilled hole. There is a hole here in the transverse direction. That is what it is saying. And the diameter of that guy is 6 mm. So it's a little bit more involved problem. We need to be very careful in understanding this problem. So what we need to do is estimate the factor of safety guarding against fatigue and static failures. Estimate the factor of safety guarding against fatigue and static failures using modified Goodman criteria for the following loading conditions. First, let's look at this loading condition, and then loading condition A is shaft is subjected to completely reversed torque of 120 Newton meter in phase with completely reversed bending moment of 150 Newton meters. Meaning what? You have a torque T. So load case A we are looking at. So load case A torque T is equal to 120 Newton meter. Completely reversed means alternating torque, and mean torque is 0. Similarly, completely reversed bending moment. Completely reversed bending moment. So sigma E, I'm sorry. Completely reversed bending moment means MA. That means only alternating stress. So there is no mean component. So M mean is equal to 0. It's only alternating component. Okay. So you have a hole. This is the loading scenario that we will come to it later. But we need to, because of the fact that there is a hole, there is going to be some stress concentration factor. And hence, you need to worry about the fatigue stress concentration factor in this particular scenario. So what do we need to compute the fatigue stress concentration factor, one thing, and what is the stresses experienced, because we are only given torques, but what are the stresses experienced by this system. So you have, if you look at the tables, I will just show you how these tables look like. So if you have a situation like this, and you know that give me a minute. Yeah. So you have a shaft as shown here, applied to bending moment, and outer diameter D, inner diameter small d, and transversely drawn hole is this guy, that whose diameter is A. Okay. So now there are a couple of things. Here you are actually looking at the stress concentration factor. Okay. And there is something called this A, parameter A. I will. So this parameter A, and this is our stress concentration factor. These are the two things that we actually need stress concentration factor, but there is something called capital A as a function of D by D and A by D. A by D is the ratio of the transverse hole diameter to the diameter of the shaft, major diameter of the shaft, and minor diameter of the shaft to the major diameter of the shaft. For different values, 0.9, 0.6, and 0, you have these values, and you need to calculate. You need to compute these two guys. We only need stress concentration factor KT, but we are also getting another A. What is this? What happens is, because of the fact that there is a hole, the amount of cross-sectional area available near the hole is not the same. And hence, your nominal bending stress should not be calculated based on the total area, but you should actually take into account of the presence of this transverse hole. And hence, normally your stress, bending stress is M by My, and that is equal to m by I by y is called z. That is called section modulus, right? But in this particular scenario, in the case when you have a transversely drilled hole, then your sigma will actually become as a function of z net, because your actual area available is not cannot be section modulus will also change. So the z net is given by pi a, this factor. So there is a factor. Normally your z net would be give me a minute. Normally your z net would be pi by 32 d power 4 minus capital D power 4 I by y will be d by 2. So pi by this will be 64 and by d by 2 then that becomes 32. So basically it should be pi by 32d capital D power 4 minus small d power 4. That is what is your normal z net, section modulus. But because of the fact that there is a transversely drilled hole, there is a factor that is coming in. That factor is what we are calling A. This is not cross-sectional area, it's only a factor A. Okay, one needs to take into account of that factor based on the values of small a by d and capital D, small d by capital D. That is for bending. Okay, coming to torsion, torsion is your tau is equal to T R by J normally. So that is T R here capital D by 2J, right? But because of the fact that there is a transverse hole drilled into the system, so this becomes J net. So what is normally J? That is J is your polar moment of inertia. That is pi by 32 d power 4 minus capital D power 4. Okay. Because of the fact that there is a transversely drilled hole, you will actually this J becomes J net with a factor A, and the factor A for torsion has to be obtained from this table, where A by D, this column, first column represents the A by D, and then different values of D by D, you can actually find out the values of A and KTS. What is KTS? Shear stress concentration factor. Okay, that is KTS. Previously, that is normal stress concentration factor. This is shear stress concentration factor. They are two different things. Okay, so if you have your small d by d value not exactly 0.9 or 0.8, then you need to interpolate between the values that you read from this table. That is what one needs to do when we are going to calculate the stress concentration factors for this scenario. Okay, so we have done that. And so if we, let's go back, and then we have done that, and then we found out for a hollow shaft of a scenario given here for bending, A comes out to be, so here because your D by capital D is that is 34 by 82, that is 0.81, and A by capital D is A is 6 by not 82, this is 42, I'm sorry. Should be 42, 6 by 42, that would be 0.143. And you would see that these values are not exactly available in those tables, so you need to do some interpolation from the data that is available. So A comes out to be 0.798 and bending stress concentration factor is 2.366. Similarly, for torsional load, A is equal to 0.89 and KTS is equal to 1.75. That's what we will get. So now, of course, before we apply these stress concentration factors, we need to find out what is the stress, bending stress that is being applied. So in order to calculate your bending stress, that is M by Z net. So we need to calculate Z net is equal to pi times A divided by 32D. So in order to make it clear, so this is bending and this is shear. I am writing like that. So just to be consistent. So pi A bending times D power 4 minus capital D power 4. and that is pi into 0.798 into 42 power 4 minus 34 power 4 divided by 32 into 42. That turns out to be 3.31 into 10 cube mm cube. All units are in mm. And similarly, if you have to calculate tau, that is equal to T D, capital D, by 2 J net. So we need to calculate J net. So first we need to calculate J net. J net is pi A. So we'll calculate J net. That is pi A by 32. A, this should be S, D power 4 minus capital D power 4. That is pi into AS is 0.89 divided by 32 into 42 power 4 minus 34 power 4. That comes out to be 155 into 10 cube mm power 4. The units are different. Please keep that in mind. So now here the diameter of the hole that was drilled was 6 mm. So the whole diameter is, the whole diameter is 6 mm. That implies radius of the hole is equal to 3 mm. Okay, so that means that is our notch radius. Why are we worried about it? Because we only got from these tables, we only got theoretical stress concentration factors. But for solving this problem, we need fatigue stress concentration factors. In order to find out fatigue stress concentration factor, we need to find out what is our notch sensitivity factor, that is Q. So Q in bending for the whole radius 3 mm and the diameter of the components, you can actually look at the tables, and then for notch sensitivity factor for bending is 0.78 and notch sensitivity factor for torsion for this particular scenario is 0.96. Okay, then your Kf, when you don't write anything, that means it is actually bending or normal component, QB into KT minus 1. That is equal to 1 plus 0.78 into 2.366 minus 1. That turns out to be 2.07. Similarly, KFS, fatigue stress concentration factor in shear, is equal to 1 plus Q, yes, I would write QS into KTS minus 1. That is equal to 1 plus 0.96 into 1.75 minus 1. That turns out to be 1.72. So now we have fatigue stress concentration factors. Now, having calculated the fatigue stress concentration factors, you would see that your you can now calculate your actual stress, that is equal to bending stress amplitude is equal to bending stress amplitude is equal to what is that? Kf times m by z net, right? So that is equal to Kf is taken as 2.07, m is 150 Newton meter, but I am writing everything in mm, so I am just in meters I am converting into mm, divided by z net. Z net is 3.31 into 10 power 3 mm cube. 3.31 into 10 power 3. Here I have put 10 cube because 150 Newton meter and meters I am converting into mm, just to be sure that everything is in Newton per mm square. So if you do that, that comes out to be 93.8 Newton per mm square, that is MPa. Similarly, this is stress amplitude in the bending. There is no mean stress, and stress amplitude in shearing, the torsional stress, that is KFS TD by 2J net, right? That is equal to 1.72 into 120 Newton meter 10 cube into D is 42 divided by 2 times J is 155 into 10 cube mm power. So that comes out to be 27.96 MPa. Okay. So now you have a multi-axial state of loading. And in this case of multi-axial state of loading, what you will do, you actually calculate sigma m is 0. There is no mean stress here. So you are only calculating equivalent stress amplitude, that is equal to sigma a square plus 3 tau a square, that is equal to sigma square root of 93.8 square plus 3 into 27.96 square. So that comes out to be 105.6 MPa. That is the stress amplitude that we have. So what is the material, by the way? It is AISI 1018 steel. So for the AISI 1018 steel, what is the ultimate strength? You can actually look in the tables. But nevertheless, first of all, let us actually look. So the values of SUT for this particular material, so AISI 1018 steel, the value of SUT can be obtained from tables, but in the exams these values will be given. But for practice, you should be able to look at the tables and obtain these numbers. 450 MPa and yield strength is 350 MPa. Okay, I'm taking this. These are the numbers. Okay, so you have SUT 450 MPa, yield strength 350 MPa. Okay, fine, that's good. So now, in order to find the factor of safety is basically endurance strength, so by alternating stress that you have. Correct. So you need to for 10 power 6 cycles, it will be if you want to have that much life, that is what will be your endurance strength, right? So now you know what is sigma AE, but you need to calculate your endurance strength. So SE dash we know is to be 0.5 SUT. That is equal to 0.5 times 450. That is 225 MPa. Correct? And now you carefully look at the statement, the problem statement. The problem statement says that it is a cold drawn steel and the shaft diameter is 42 mm. And hence you need to account for correction factors because the shaft diameter is not 8 mm. Because if it is greater than 8 mm, you need to account for the C size correction factor. Similarly, depending upon the process, you also need to apply the surface finish correction factors. So these are the things that we need to account for, and hence you cannot right away use SC dash. So you have to use your SE after applying correction factor, size correction factor, and surface finish correction factor, because other information is not available, and hence we assume the other things to be 1. Now C size. In the exam, we will give you these correction factors, or we will provide you the formula. Okay, that is so. If you are given the formula, you will be able to substitute the values and then be able to calculate the values. So C size is equal to 1.189 times D power minus 0.097. And please keep in mind, this is the way that we are writing our C size formula. Here, which D I have to take? Just because I have written small d, you should not take small d in this problem. Because here you are talking about the shaft diameter, so the outer shaft diameter, because the fracture can happen because the inner diameter has no meaning. So outer diameter is the total diameter that we have. So you need to take into account of that diameter. Okay, so that means 1.189 into 42 power minus 0.097. That will give me a C size factor of 0.827. And the C surf is ASUT power B. Okay, so if you would see your A and B parameters for your cold drawn condition, so let us see that. Yeah. So cold rolled sheet has, when your SUT is given in MPa, then your A is 4.51, B is minus 0.265 with SUT. So A is equal to 4.51 times SUT is 450 MPa divided to the power minus 0.265. Okay, so if you do that, then it becomes 0.893. So you have the size factors into this problem, and then having calculated the size factors, you can calculate your corrected endurance strength is equal to C surf C size times SE dash. So C surf is 0.893, C size is 0.827 into SE dash is 245 if I am correct. Yeah, 225. So plug that in. So 225, and that comes out to be what? Let me check. 0.893, 0.827 times 225. That comes out to be 166.2. 166.2 MPa. So that is your SE. So the factor of safety will be SE divided by applied stress amplitude, right? Sigma AE, equivalent stress amplitude. SE is 166.2 divided by equivalent stress amplitude. What is that we have calculated? 105.6 MPa. So 105.6 MPa, that will be what? 166.2 divided by 105.6 will give me 1.57. And so this is your factor of safety in fatigue. Now, you are also asked to find out the yield factor, sorry, the static factor of safety. So there is something called the first cycle. In the first cycle, the first cycle yield factor is, that is NY I am calling, is yield strength of the material divided by the stress amplitude. That comes out to be about 3.5. So what basically it means is that in the first cycle, the material is subjected to this particular stress amplitude 105.6, and your yield strength of the material is 350. And that means this guy is not reaching the yield strength of the material in the first cycle, and hence there will not be any localized yielding. So there will not be any localized plastic deformation, and hence, because we are using the HCF, so the expectation is that the threat, so the hence there is no localized yielding, and the threat to failure is from fatigue, because the yielding factor of safety is much larger. So the mainly it will fail, if at all it fails under fatigue, because it will, before it reaches yielding, it will reach its life based on this loading. So first it will fail in fatigue. Okay. All right. That is for the first case of loading. Now let us look at case B. Okay. So let us look at case B. What is the case B loading? Let us see. The shaft is subjected to a pulsating torque fluctuating from 20 to 160 Newton meter and steady bending moment of 150 Newton meter. That means the torque is fluctuating from 20 to 160 Newton meter. So let us say this is 0, and let us say this is 20, and that is 160. It is fluctuating between these two. Right? That is the torque. This is the torque signal. So it has some mean torque and TA. Okay, amplitude. So what is the mean torque? Mean torque is 0. So we have to calculate what is our mean torque. Mean torque is 160 plus 20 by 2 that is 80, 90, 180 by 2, that is 90. That is 90 MPa. Sorry, not MPa. Mean torque 90 Newton meter. And alternating torque is 160 minus 20 by 2, that is 140 by 2, that is 70 Newton meter. And you have a steady bending moment. That means bending moment, if it is steady. That means it is not changing. That means it is mean bending moment. So that means M mean bending moment is 150 Newton meter. That's what we have. So using your shear stress amplitude is equal for the same problem KFS torque. I would not put here shear stress amplitude TA d by 2 J net, not Z net, J net, right? This is alternating component because we are calculating alternating component of the stress. That is 1.72 times. This is 70 times 42 divided by 2 into 155 into 10 cube. Here 70 Newton meter, so and hence I have to put 10 cube here because everything I am keeping it mm. So that comes out to be 16.3 MPa. Similarly, the mean shear stress is KFS TMD by 2 J net, that is 1.72 into mean is 90 into 42 into 10 cube. This 10 cube is coming from 90 by 2 into 155 into 10 cube. That is basically 20.97. The bending moment, only mean bending moment. There is no alternating component. So the mean normal stress is equal to Kf times mean bending moment divided by Z net. So that is equal to the, here I am using KFS, that is shear fatigue stress concentration factor. This is normal or bending fatigue stress concentration factor into 150 into 10 cube divided by 2, there is no 2, sorry, 3.31 into 10 cube. 3.31 into 10 cube. That is equal to 93.8 MPa. Okay. So your let's go to the next page. So now you have tau A, tau M, sigma M. Now it's a multi-axial state of loading and hence you need to calculate equivalent stress. So mean equivalent stress is equal to square root of sigma M square plus 3 tau M square. Similarly, alternating equivalent stress is equal to sigma A square plus 3 tau A square. Correct? So this is equal to square root of sigma M is 93.8 square plus 3 into 20.97 square. Whatever that value may be. And sigma A equivalent, there is no alternating component of the normal stress, that is 0 plus 3 times tau A is 16.3 square. Okay, this value sigma M equivalent comes out to be 100.6 MPa and this comes out to be 28.2 MPa. So what we have is now sigma M equivalent is 100.6 MPa. Sigma A equivalent, that means alternating stress component, is 28.2 MPa. So now we are asked to find the factor of safety because you have the effect of mean stress. Then now we need to use either Goodman criterion, Soderberg criterion, or Gauss parabola. One of these criterion one needs to use. Okay. So now according to Goodman, n equal to, so this is Goodman I am writing, SE SUT divided by sigma ME SE plus sigma AE SUT, right? So that is equal to SE we have calculated 166 point what did we calculate? SE 166.2 into SUT is 450 divided by 100.6 into 166.2 plus 28.2 into 450. That is what is your N. So that turns out to be factor of safety. Let me calculate. 166.2 times 450 divided by 100.6 into 166.2 plus 28.2 into 450 comes out to be 2.54. So the factor of safety in fatigue is going to be 2.54. So let us actually do some analysis here. Okay, I will just would like to do some analysis so that we understand what do we mean by how can we comment on the static failure as well from this data. Okay, so now let me draw the sigma m sigma a plots. Okay, I'm just drawing it to scale. So each one is 25, 50, 75, 100. So let us say this is our 100. 1, 2, 3, 4, 200. 1, 2, 3, 4, 300. 1, 2, 3, 4, 400. 1, 2, 3, 4, 500. Okay. So I'm writing this is 100 MPa. This is sigma m, right? On x-axis. 200, 300, 400, 500, and this is our 450. Similarly, 100, 1, 2, 3, 4, that is 200, 1, 2, 3, 4, it is 300, 1, 2, 3, 4, that is our 400, and this is our sigma A stress amplitude. Now, let me draw the Goodman line. So how do we go about drawing the Goodman line? So the Goodman line comes from on this you will have SE. I have to identify SE. What is my SE? 166.2. So on the y-axis, so I'm on the y-axis it is 450. So that my point is that on the x-axis 166. So this is 150. So I'm just going. This is 175. So I'm just going halfway through. That is my Goodman line. So the point on the Goodman line. So now I connect those two guys. That is my Goodman line. Good. Now there is something called yield line. We have not paid attention to when we were discussing in the class, but now I think this will be really helpful. What is yield line? Yield line is actually connecting a line, the line connecting the values equal to the yield strength, both on mean stress line and stress amplitude line. What is the yield strength of the material? This material's yield strength is 350 MPa. That's what we have seen. Okay. So now this is my, so yield line is shown with blue color in here. It is, oh sorry, that is my 350 and that is another 350. So let me draw that with the blue color. Oops. That is my yield line. So the green is yield line. And now let us look at the two states of stress. The case A. Case A, what is our, this is case A. Yeah. Case A, our material did not experience any mean stress, but only alternating stress, right? So if you would plot that, so this will be 100, this is 125. So this will be, so I'm showing that in black color. Okay, that is 105.6. That is our case A. So if you would actually, let us say you are moving along, this is the load line. So now if you have to connect, so the load line starts from O and go up to 0.1. O1 will be your load line. So if you are continuing in this load line, you are actually hitting the Goodman line first. That means the material is, if at all it is failing under this loading, it will only fail due to fatigue. That means the fatigue failure will occur first. And now let us look at the second one. What is the second state of stress? This is 100.6, 28.2. 100.6, very much close to this guy. So I would show that in black color. This is 100.6 and 28.2. So this is 25. This line is 20. Here it is 25. So 28. This is 50. So I'm just showing it as 28.2. So that is the point. Correct. So that point is my point 2. That is the loading. So now let me draw a line joining those two, because that is my load line. Okay, that's my load line. Now again, if you actually move along this line, your failure to due to fatigue happens here, and here it is hitting the yield line. Okay, now so that means here also the material is expected to fail under fatigue, right? The material is more susceptible for failing under fatigue. So now let us see under Goodman criterion. According to Goodman criterion, the material is susceptible to failure under fatigue. Now, if I would draw a Gerber's parabola, means another failure criterion. Let me draw that using another color just to make it. So the Gerber's parabola would look something like this. Okay, that is your Gerber's parabola. Now, so if your failure criterion is not Goodman but Gerber's parabola, you would see that the failure is happening at this point according to Gerber's criterion. Okay. So along this line, this is actually this line, but the failure according to Gerber's parabola happens at this point. And let's say you don't have the Goodman criterion, then this loading line is hitting the yield line first and then hitting the Gerber's parabola. First it is hitting the yield line and then hitting the Gerber's parabola. That means in this scenario, it is possible that the material might experience failure from notch yielding. That means at the notch in the first cycle of loading, the material might actually experience, if this is the kind of a loading scenario that you are going to have, the material might actually experience notch yielding because first this yield line is hit rather than the Gerber's parabola. So, but however, if you are using Goodman criterion, you would see that it is hitting the Goodman line first, and hence you would not expect notch yielding. Whereas when you are talking about Gerber's, if your criterion is Gerber's parabola, you would expect notch yielding. And you know that Gerber's parabola is a little bit better approximation to the actual failure of the material compared to Goodman criterion. But Goodman criterion is simpler to apply, and hence we are using Goodman's criterion. Okay, so that is how you can actually use this yield line to make comments on the static failure in scenarios in the case of when the material is subjected to dynamic loading. That means whether there is going to be some yielding or not in this scenario. So here, according to Goodman criterion, the failure may first come from fatigue according to Goodman criterion. However, according to Gerber's parabola, Gerber's criterion, failure may first come from first cycle notch yielding because it is hitting the yield line first. If at all it goes along that direction, it will first rather show yielding, notch yielding rather than complete failure according to Gerber's criterion. Okay, so I think with that, we've actually see the way that we have done in this class is the following. First, we have looked at the multi-axial loading scenario without any notch. Then we have actually looked at the situation of one-dimensional loading, but in the presence of notch. What is the effect of? How do we take into effect of the notch or stress concentration factor? Then what we have done was we have actually used notch and the multi-axial loading scenarios, and then to see how, and then we are also able to add another complexity to explain about the notch yielding, whether the notch yielding will be prevalent in the material or not. I hope these three problems I've given you some understanding of how do we go about solving multi-axial fatigue problems, and also how do we go about taking into consideration of the presence of notches in the material. With that, I'll stop and thank you very much.